This video we're going to talk about Ohm's law, power equation, heat and resistance. Now you may have seen these kind of circuits in the first year and you've probably solved a few. But what this is representing is a rig that I've built, and it's two light bulbs wired in parallel. So we'd have the live coming down here and then splitting down there, and then the neutrals carrying it away. Now the bulbs I'm going to use are these kind of old filament bulbs, and they're rated at 60 watts at 240 volts, and that'll be important later for a fair comparison. 240 volts was the old nominal voltage. Nowadays it's 230 volts. Details on the screen now. But yeah, so for purposes of accuracy on this calculation, I'm going to use 240, and we're going to calculate the current here, and we're going to measure it on the rig, and then talk about why it didn't work. So what I've done, I've measured the resistances of these bulbs, and I've actually measured quite a few, and they do vary a little bit from like 68 up to 72 in fact. So for the purposes of simplicity really, and a fair average I'd say, I'm going to use 70 ohms because it's just nice and simple. It's not really about parallel equations, this video, you can look that up later, but yeah, let's calculate this. So, you know, to get your total resistance in the circuit, you may remember it's, you might have seen it a few different ways actually. It might be, sorry, come on, 1 over R1 plus 1 over R2 and 1 over all of that to get your total resistance. Or it might be, depends what book you're using really, R1 to the minus 1 plus R2 to the minus 1, all inverted. Those mean the same thing. Has my rubber gone? Oh, it's gone. Brilliant. Oh well, it needs a wash anyway. But there's actually an easier way in this situation. Just understand that whatever current's going down here, we've got two barriers in the way of it, and they're both equal. So whatever current is coming along here, it's going to split equally. So, you know, flip that on its head, the resistance is going to appear to be half of one of those, because whatever these barriers are, we can divide them by 2. So to get our total resistance, when you've got parallel resistances and they're all the same, you can just take the value of 1 and divide it by how many there are. So in this case 2. So our total resistance will be 35 ohms. And from that we can calculate IT, the total current in the circuit. And that'll be just Ohm's law. So we take the voltage divided by our resistance, and we can calculate our total current. So 240 over 35, so 6.86 amps. Now if we wanted to calculate current in these two, we said earlier, this will just split equally into 2. Or you can use Ohm's law again and call this one I1 and that one I2, and it'll just be the voltage divided by the resistor that we're concerned about, so 70 in this case. And I2 would be exactly the same calculation, so 240 divided by 70. Let's see what that is. Yeah, so it's going to be 3.43. So yeah, just split. So we're happy with that. And that is accurate for these resistances with that voltage, but let's just stop and take a sec to think about this. We've got two lamps which are rated at 60 watts and it's pulling 6.86 amps. Doesn't sound right, because in our lighting at home we used to have maybe 5 or 6 of these on a lighting circuit, and it used to be protected by a 5 amp and then eventually a 6 amp. So something's not right. So let's go to the rig, actually measure it, and then we'll come back to the board and explain why it didn't really work. So this is the rig in all its glory, and what we got is lights in parallel, just like we had on the board. I'm only going to use 2 of these, I'm not going to use this third one. Reason being because I stupidly told my students there was only 2 lights on the rig, so I don't want them to get confused with different values. But you know, the comparison will still be the same really. It will still prove the same point. First, let's just measure the resistance of one of these bulbs and just kind of prove where I got that value from. Now this is quite tricky to do. I don't know if you can see that. Don't want to push too hard in case I smashed the bulb. 67.4. 67.4. Now I've tested a few of these, and there are tiny little differences, probably down to how hard I'm pushing. Let's see if I can get a better reading on this one. So that one's a little bit less, and the other one I did earlier was a little bit more. I was saying 70. So there's tiny little manufacture variations there, and that's just life really, I suppose, isn't it? There's always tolerances with these things. So what I'm going to do, I'm just going to liven it up, and I'm going to record the current with the clamp meter, and I'm going to record the voltage, and then yeah, we'll just see how that compares. I've got a secondary clamp meter here, purely because, you know, this one's quite new, so it should be okay. I've hardly really used it. This one's really old, and I was just interested to see how it compares really, and see if it's still any good. So let's stick those. We'll do current first. Just put these bulbs in properly. So as you can see, it's like the circuit on the board. We've got the lives coming down here, and then it's branching off in these directions, and then the neutrals coming back and taking the current away. So let's see what we got. 0.22 amps through that branch there. Let's see what it is overall. I've got 0.47 amps there. I'm just going to try the other one. Go around the neutral, it should be the same. This one only has one significant digit, so it's saying 0.4 still. So it's not quite as accurate, that one, when we're talking about things like this. Let me put it in the same place, see if there's any difference, but I doubt it. No difference, still saying 0.4. And this one is still saying 0.47 amps. So nearly half an amp going through there. And we'll just check the voltage. So what do we think? Now I know that this area is quite high voltage on these leads. I'm not a fan of the rubber leads, I've got to say. They just twist up so quick. Oh my days. They're horrible. One in there, one in there. 241 volts. 241 volts I'm getting. So not quite the 230 we were expecting, but that doesn't matter. We've got flex with that value. So that's what we're getting. 241 volts and 0.47 amps. So let's go back to the board and see how that all compares. Yeah. So there you have it. Quite wrong. We had predicted that the current in the circuit would be 6.86 amps at 240 volts. The actual was 0.47 amps, and we saw that, you know, it was about half that in each of the branches. So what happened then? Well, the thing is that I measured this at, it was about 20 degrees. So let's just see what it is. So it's 21 now, but you know, it's a bit warm still. And that makes a big difference, because as soon as we apply the voltage to it, current flows and the filament heats up, and that's how it gives off its incandescent light. And that filament gets hot, and I mean really hot. And the thing is with resistance is that when the temperature increases, the resistance increases. And it's actually quite predictable. So copper, for example, increases by 0.00393 ohms per degree centigrade. Tungsten, well, let's have a look, shall we? So we can see there that copper rises by 0.00393 ohms per degree, and tungsten is 0.0044. So what can we do with that information? Well, there's another equation we can use to predict the resistance based on that information at the kind of final temperature. Let's just tidy this up. So, what could that be? Oh, I want that circuit later, damn it. I'll leave that. Well, the equation is our final, if you like, is equal to RO 1 plus alpha delta T. And a lot of my apprentices just what? There is a slightly easier way of writing that actually. It's R final will be equal to RO, so this is the original resistance at 20 degrees, and then plus minus, I'll stick to plus one, the original resistance times that coefficient times delta T. Now, what is delta T? Delta T is change in temperature. So if it's going from 20 degrees up to the final temperature of this filament, which is actually about 3,000 degrees, then our change in temperature would be 2980 degrees. So let's put in the figures that we had earlier. So the tungsten filament was 70 ohms, and we're going to add that to 70 ohms times this coefficient, so 0.0044, times that change in temperature, 2980. And what we should get is a more realistic resistance based on its final temperature. So let's see what we get. 7E plus 7E times 0044 times 2980. So 987.84 ohms. 2980, yeah. Just check what I'm doing nowadays because I misread things quite a lot now. As I'm getting older, my eyes kind of blur things out, and I think I make it up in my head sometimes, you know. So just double check. Yeah, 987.84. So the resistance of the bulb when it's running hot is more likely to be somewhere around there. So let's just redraw that circuit and see what happens if we put in that figure. That's per bulb. So our circuit was like that. Like that. And now we've got 987.84 ohms, and the same here. And we'll stick to the original 240 just for now. I mean, 241's not going to make a massive difference, to be honest. So parallel resistance then, we got 987.84 to the minus 1 plus 84 to the minus 1 equals, flip it again, 493.92. And again, we could have just taken one of them and divided by 2. So our RT is 493.92 ohms. And obviously we're not counting the resistance of the copper wire there, but it will have an effect, but negligible in this case. So then 240 volts divided by that, 493.92, gives us a current value. So our IT, that one, of 240 divided by 493.92 ohms equals 0.49 amps. So much closer, and that's what it is. That's why it didn't work, because I used the wrong resistance, used the cold one. So what's really going on in that circuit, because it does start cold, and so what you'd end up with, if you had like a current time graph going on, then you'd get like an initial spike, and then it kind of settle down as it heats up. So what we're really saying, as a conductor heats up, the resistance is going to increase. It's a really important concept for electricians to get their head around, especially in design and testing. Talking about max ZS and R1, R2s, it's important to get that right. So there we go, really. But this is kind of madness, isn't it? This isn't how we work out the current in the real world. There's a much simpler way, and it's the way we actually do it. Because the manufacturers have kind of sorted all this out, really. And they give us everything we need to know. They give us the wattage, and they state what voltage they calculated that with. And that's important. Now, I've already said 240 volts is the old nominal voltage. Nowadays it's 230. But we've got an equation that we can use. And that's power equation. So P in watts is equal to the volts times the current. Now it's important to recognise, is that too high for you? No, I think you can see it, that this is all in one system. we can't just put in random numbers and expect accurate answers. So we always need to know two known values, or two measured values, and then we can calculate the third. So in this case, they've given us the 60 watts, and they said they got that when they applied 240 volts to it. And so we can calculate the current that we would expect at 240 volts. Bit of transposition, so let's just get rid of that 240. It's being multiplied, so we're going to do the opposite function by itself, which is divide by itself. We've unbalanced the equation, so I'm going to rebalance it by copying it. Then looking back, this is now balanced, but 240 divided by 240 equals 1, and 1 times I equals I, so we don't need it anymore. And our new equation is this. And even me, with my limited maths abilities, can tell you that 60 divided by 240 is a quarter, or 0.25. And so if we had 2 lamps, we times 2, and that's a half. So that's half an amp. And we predicted 0.49, was it? So this way we would have got half an amp. Much quicker, isn't it? And isn't that nice? So in the real world, this is what you're going to be doing. And it really does. It doesn't really get much more complicated than that. Let's write the actual equation. So if we're doing design currents to calculate, cable sizes and stuff like that, it's really is as simple as that. Well, I mean, it gets a bit more complicated if you've got a power factor. Just times it by the power factor. Brackets. But that's it. That's about as complicated. Well, not really, because if it's 3-phase, then it's a little bit different again. But I'll just show you. So you'd use 400 volts instead of 230, or U, as it's known, line-to-line voltage. And then you times that by √3, and then times the power factor. And that really is about as complicated as it gets. And that'll give you your design current, or IV. That's the end of this video, really. Bit of a waffle, I suppose, but I hope you can keep track of the point. And the point is that as the temperature increases, the resistance is going to increase. Incidentally, you can do the equation the other way as well, so if it's decreasing in temperature. And for that, you would have R final equal to RO, so the original at 20 degrees, minus RO alpha delta T, all multiplied. Now it's the end. See ya.